Hello, everybody. My name's Tim King, and I've got Louise Turner here. Louise is pretty epic, so I thought that would be a really good way to introduce quantum to you because we've both kind of worked our way into this in an interesting way. So today we're going to talk to you about the world of quantum advantage. Quantum sounds like something from Marvel, but it's actually much more interesting than that. So I'm a teacher. I teach in Ontario, but right now I'm seconded to ICTC and I'm doing education outreach nationally, mainly focused around cybersecurity, but I'm trying to expand that to include things like quantum technologies.
And hi, my name is Louise Turner. I'm a former student of Tim and also a former CyberTitan national finalist. I currently attend Queen's University. I'm in my last year of my computer science degree with a cybersecurity specialization, and I'm a Schulich leader. So in my time in high school doing CyberTitan and other techie things, I ended up applying for a scholarship, which is the biggest STEM scholarship in the country, and I got it.
All right.
And yeah.
We didn't just do this. Like we went everywhere. That's us in Ottawa, the picture at the bottom. Love that picture. We actually hacked the screen in the background, remember?
Oh yeah. We did.
Been in the news too. So
Yeah.
that's a good thing there. So what we're going to do is get into quantum here a little bit, and Louise is going to take the lead and walk you through because she's been neck deep in quantum for the last year, working with the Quantum's Algorithm Institute.
Yeah, so what is quantum? We've been working with quantum for almost a century. The year 2025 was chosen as the International Year for Quantum because it recognizes 100 years since the initial development of quantum mechanics. And quantum is essentially the study of really, really small things. So absolutely microscopic stuff. It isn't super science fiction-y. It's something that you can understand yourself, and it's all based in physics.
We're trying to get you away from that whole Marvel view of quantum.
So where's the Canadian government on quantum? Well, quantum, because it's a study of very small things, it touches a lot of stuff within our electronics and within all of our technology. So this is a quote from Minister Champagne where quantum is not vertical, it's horizontal like AI. So you know how AI is basically touching everything within technology at the moment? Quantum is eventually going to become like AI, touching everything we're doing in little ways. So why do we have the fuss now if it's been over or just about 100 years since quantum has started being studied? Well, in 1925, quantum mechanics was all discovered. We started doing all these different things with it. One of the big things we're doing with quantum computing is, or just quantum in general, is MRI scans, stuff like that. And you can see that the electronics that we have started using, so the electronics that are in your computers right now, have started getting super, super small. So that little image on the right there is an electron microscope going into a computer, and it can show how absolutely tiny all the little components of computers are. And as we said, quantum is a study of very small things. So as we go deeper and deeper into these computers, we have to start looking at things from a quantum perspective. So we talk about there are kind of two eras of quantum. There's quantum 1.0 and 2.0. So quantum 1.0 is how we leverage quantum naturally. So as I mentioned, we use it during MRI scans because quantum is everywhere. It's always everywhere. It's naturally occurring. But quantum 2.0 is where we start leveraging that more and really taking advantage of it.
If we have any science nerds watching, I'm a big Brian Cox fan, and he has a great quote in the previous one where he says, "It's not Newton for big things and quantum for small things, it's quantum all the way." So if you're learning classical physics, that's sort of the old school physics. You can do all the same things in quantum more accurately, and that's where we're at right now.
So quantum tech is all around us at the moment. Like we said, MRI scans in our computers. Our computers have started getting super, super small with all the transistors in our computers. So we've started to have to think really tiny. And yeah, Quantum 2.0, different from Quantum 1.0, rather than just utilizing quantum being around us all the time, we're actually trying to manipulate it and use it properly to our advantage. So engineering quantum effects rather than just letting them happen naturally.
Maybe a good way to think about that is resolution. So if you play video games, you know how a really high resolution 4K or an 8K game looks so much sharper. Our quantum technology is going to that level of fineness. So instead of thinking of about old school science and sort of Newtonian physics and things like that, this is physics as it actually happens, but it's very complicated and takes leading edge tech to get to.
So what is quantum computing? Well, it is leveraging quantum mechanics to do computing. It's very different from regular computing, as we'll get into, but you can see this little animation here. You often see quantum computers looking like these crazy massive things full of pipes and stuff. And that is basically what they are, but as you see it zooming in there, the actual quantum computer part of it is a very small chip, and that massive big thing around that small computer chip is actually the cooling system for it. So it helps it get super, super cold so that we can manipulate those quantum effects to do what we want.
I went to a UBC quantum training week last year and I got to go inside D-Wave and they had one of the computers open because they were changing the CPU. And that CPU is inside a whole bunch of shells, almost like Russian doll nesting shells. And in the middle one, it goes down to minus 270 degrees, which is almost absolute zero, which is incredible. But you need to be that cold to get these computers to work. This is state-of-the-art stuff.
So how are quantum computers different from regular ones? Well, you can think of regular computers as working off of ones and zeros. So they're made up of a bunch of really tiny circuits that are either off or on. And from those tiny little circuits, you get to do all the mathematical functions that allow your computer to work. Now, quantum computers work with ones and zeros, but they also work with all of the tiny numbers in between those ones and zeros. So we can say that they leverage probability rather than being deterministic. So deterministic being 1 and 0, probability being it's 50% chance of being 1, 50% chance of being 0. And because of this probability of using every number in between 1 and 0, they work on an exponential scale. So they work super, super fast rather than on a linear scale like a regular computer. And quantum computers can use a lot of different kinds of materials to make calculations. So the main part of a quantum computer that makes it work like regular computer is called a qubit. So you can think of that as a bit in your regular computer as being a 1 or a 0, but qubits can be made out of so many different kinds of materials. So there are superconducting qubits, there are ion traps, defects in solids like diamonds. They use actual diamonds and the defects within those diamonds to make these qubits and make these calculations.
So it's like computers we have now, but not as you know it.
Yeah, so why did we, like Tim and I, have this interest in quantum computing specifically? And it is because of how it intersects with cybersecurity. So quantum computing, because it is super powerful and super fast, it can be used for a lot of amazing things, but also if it gets into the wrong hands, it can be a big threat to cybersecurity. And you see that the NSA actually is a bit scared of quantum computing and they're trying to prepare for it.
The quantum revolution, when's it coming? That is the big question everybody's concerned about right now. My favorite quote was from the head of photonic in BC, and he said, "I think we're 4 years out, and if I'm wrong, 3 years." So whatever you think the timeline is, it's probably coming quicker than you think.
So the big thing with quantum and how it's a threat to our cybersecurity is something called RSA encryption. Now, RSA encryption is an encryption method that's used in a lot of what we do on the internet today. So about 90% of all the communications you're making on the internet every day are going through RSA encryption. Now, very simply, RSA functions using prime factorization. So you find a number, and then you want to get what two prime numbers can you multiply together to make that number. So we see with the number 72 here that it's just a couple steps. You can do it on a piece of paper. It's really easy to find that prime factorization. But RSA uses numbers that are 617 digits long. then you need to find the prime factors of those numbers. So it can take 300 trillion years for a regular computer to crack RSA, but a quantum computer could crack it much faster. So how do they do that? They do it with a quantum algorithm. So you have all the hardware for a quantum computer that makes it run, but you also need to be able to code and make the algorithms for quantum computers. Now, how quantum algorithms differ from regular ones is we can see in the little animation here. On the A side, the little dot goes through the maze one step at a time, whereas on the B side, it tries every path at once. And that is the big difference between quantum computers and classical computers. Classical computers try every step one at a time in sequence, whereas a quantum computer can try them all at the same time in parallel. So this is where we start getting pretty crazy. And how can we use these quantum computers and quantum algorithms to potentially break RSA encryption? So as we said, RSA encryption focuses on finding prime factors. So a way that we can utilize quantum algorithms and quantum computers is by using Fourier transforms and then making them into quantum Fourier transforms. So a Fourier transform, if you're wearing noise canceling headphones right now, what a Fourier transform does is it picks out the treble frequencies that go into your headphones and then gets rid of them so you can cancel out the noises. So it takes a sound wave and breaks it up into its individual parts. So if you're trying to factor something, which is breaking it up into its individual parts, using something like a Fourier transform is very useful. And then we go into Shor's algorithm, which uses that quantum Fourier transform. So we have prime factorization, which is breaking things into its little individual parts. And then we use Fourier transforms to find the patterns in those prime factors. So when you find those patterns, it becomes a lot easier to break it. So you have a massive, really big number that you need to find the prime factors of. Well, if we find the pattern of the different remainders in all the numbers before it, then it can be pretty easy to find what the prime factors of that number are.
And if you know anything about computer history, when Intel came out with the 4004 chip, that was the moment where computers could suddenly do a lot more. And this is the math behind it. We've figured all that out. We've got early quantum computers working, but they're very noisy. And what we're getting to now is the point where we're about to see that moment where we start to see chips come out that will be able to do this on a much larger scale. I think at the moment, Louise, you said that this is incredibly small, like they can do 15. Like,
Yeah.
yeah.
So about 20 years ago, I think it was IBM managed to factor the number 15. Just recently, there were more progress has been made in Shor's algorithm in quantum computing. I can't remember exactly what it was, but there were larger numbers that have been factored just very recently, a few weeks ago.
We need to get to, thousands long
Oh yeah.
digits to do
Oh
this.
yeah.
But what'll happen is the technology will figure itself out. And you know how quickly computers came on. It'll be the same here. Once we've figured that mechanism out and we understand how to build them, we'll rapidly improve the tech. So yeah, this is coming much sooner than you think it is.
So how can we defend against this? So if RSA is being used in 90% of our internet communications and RSA is broken, then we have a big problem on our hands. You know, a lot of data is going to be leaked, but quantum secure encryption is basically our solution to this. So NIST has been testing quantum resistant encryption since 2016. They've had a competition to see who could make the best quantum secure algorithm, and we've narrowed it down to 3 at the moment that were just released recently. And these 3 encryption methods are basically designed in a way that they can be secure to quantum computers. So although quantum computers are very fast and very efficient, there are lots of tasks that they're not good at. So we are leveraging those tasks that they're not good at to make secure encryption algorithms. Now, a fun fact about these encryption algorithms, you can see they have names here like MLChem, MLDSA that are very, they just stand for what they are. So module lattice-based key encapsulation, very boring names, but they used to be called Kyber, Dilithium, and Frodo. So those are the 3 names for these encryption algorithms. So you can definitely see that as you get older, the nerdiness of being a computer science person doesn't go away.
It does not. The fun fact as well is we had 4 of these walking into the presentation Louise and I got to do last year in Africa. And as we were walking into our presentation, we had to cut one because somebody had figured out how to crack it. So this is leading edge stuff. It's still evolving, but at this point, NIST has worked out quantum resistant standards that it thinks will last. The crypto apocalypse. This is my favorite slide, only because I made that GIF. What we've found is a lot of people are really worried about what's coming with the quantum from a cybersecurity perspective, but there are a lot of other really positive aspects of quantum to come out. In the next slide, we're going to talk about the amount of money involved, but maybe you can kick it off, Louise, by talking about all the good sides of quantum and all the things these completely new ways of computing are going to do for us.
Yeah, so quantum, although it's very powerful, can be used to break encryption. There are many amazing reasons why we are utilizing it, and one of the big ones is that quantum computing is very, very good at optimizing problems. So you might have heard of the traveling salesman problem, which is essentially trying to get a traveling salesman to go to a bunch of different points in the most efficient route possible, which has been deemed as a computationally impossible problem to solve. But with a quantum computer, you can solve it pretty easily. And there are a lot of different optimization problems like this with supply chain and delivery trucks, things like that, that have been a lot of work's been going into them. And we can see on this chart here just how much money is going into quantum development. Now, these numbers are quite out of date at the moment because Australia, you can see, said 98 million, but that is now at 1 billion Australian dollars because they just recently dedicated 900 million Australian dollars into quantum development. So there's a lot of work going into quantum development to try and make these computers more viable.
And if you want some other use cases, when I was at UBC last year taking our quantum intensive week, we had PhDs coming in from all sorts of different areas, including healthcare, where one of the researchers said if we have a functioning quantum computer, it would be able to look at your DNA, look at your cancer DNA, and actually calculate a custom solution where you would take a customized medicine that would resolve your cancer. So there are all sorts of use cases for this. Louise and I came at it from cybersecurity because that's where we work. But there are a lot of ways you're going to see quantum computers when they come online radically change how we do things for the better. So this isn't all doom and gloom. There's a lot of good to this.
So things in the quantum world change incredibly quickly. Every time we've presented on quantum computing, we have had to change our presentation because news just keeps coming out. So as you know from AI, from the boom of AI, it really progressed very slowly. If you remember those chatbots that were around in like 2013 were really, really bad, and then suddenly something clicked. We realized something, and then the linear curve turned into an exponential curve, and now AI touches absolutely everything. And that is likely what's going to happen with quantum. Something will click, and then suddenly it progresses at light speed.
And one of the things that's accelerating it is AI, because people can put in simulations now and let the AI iterate the simulation and see what works. So we're seeing rapid improvements in quantum computing right now. And when these things start to produce answers, they'll be so complex that we won't understand why it's giving us the answer it is. So, which I think is really cool from a philosophical point of view.
Yeah, things change very, very quickly, even just this month, even more news. NATO has been coming up with a quantum strategy, so quantum is being used in military a lot at the moment. I actually have friends who are in the Canadian military, and they've been talking about how there are some quantum courses that are available to them, just like introduction stuff. So it's really touching every sector in the world at the moment, and is progressing very fast.
General feeling we've had, because Louise and I have been looking into this since last summer when we did the research that led us to Ghana. And what we found was wherever you think this is going to be in 6 months, it's somewhere else entirely. It really leaps forward quickly. So if you think this is science fiction, just wait 6 months, and you might be shocked at what you're seeing. I
Yeah,
think the
so
quantum
quantum.
AI one is the one I'm
Oh
most
yeah.
curious about. What do you think?
Yeah, so quantum and AI work very well together. One of the things that we're seeing more and more with quantum computing is that it works best when it is combined with something else. So combined with classical computing, or in this case with AI. So quantum and AI complement each other fantastically because a quantum computer is great at optimization and AI needs to be optimized. So AI produces a ridiculous amount of carbon emissions, but quantum computing can help bring those emissions down. Now, on the AI quantum zone there, we have quantum computers have a lot of errors in them. That's what Tim was saying when he said they're noisy. So sometimes the readings from quantum computers can't be super precise. So AI can help fast track those errors, correcting those errors. So they work incredibly well together and they can be used to solve a bunch of different problems. So we already use AI to help with things like molecule simulation, so simulating very complex molecules. And we found out that quantum computers are great at simulating molecules. So when you put those two together, you have a whole new realm in chemistry and pharmaceuticals, drug discovery, things like that.
I think a good way maybe to look at it is the digital stuff is kind of a simplification, right? By its nature, you're reducing everything to ones and zeros, and we've done incredible things. I mean, look what we're doing right now. But that digital is really deterministic, and it's not how the universe works. So what's cool is we're actually leveraging the mechanics of the universe at the very edge of what we understand to do computing here, which is next level stuff. I love that from I'm a science fiction nerd way back. So for me, that just feels like the future, and it is going to be the future. These are our links and resources, and that URL will take you back to this presentation if you want to chase down the links. We highly recommend you look into quantum. Louise and I have been neck deep in this for about what do you think, 18 months now?
Yeah.
And I mean, it changes daily. We've done presentations on this across Canada and around the world. People are very curious about it. And if you wanted to think about something future friendly to do when you graduate from high school, you would be leaning into what's coming next if you considered anything to do with quantum technologies.
For sure. Yeah, these ideas, biggest thing I want to leave to everyone is that these ideas are not beyond you. Things like quantum, things like cybersecurity, they are all well within your grasp and within your knowledge. You just have to go out and learn them, and you can learn a lot about them if you just try.
Right on.